Hello everyone, so welcome back. I believe we have been discussing a relevant practical problem, right? And I think here the case was we are adding FeCl3 as the flocculant, right? And in the initial case or part A, we looked at a simple scenario as in what's the pH and what's the total amount that precipitates out or the total amount of iron that's present in the solution in the dissolved phase, right? So with that we are done, but part B slightly increases the complexity in that it tries to mirror some of the aspects of water quality that would actually be present in nature. So what is that? Obviously, so here now we have a new aspect as in we have alkalinity 2 present, and which is what you would usually expect, right? Alkalinity is ever present in your water or wastewater, so this is something you should usually consider. And let's see now, let's say how that's going to affect our particular calculations, right? So obviously again I think the same aspect, but with an additional aspect of alkalinity is present and initial pH is 8.3, right? And so here also alkalinity is only due to dissolved or inorganic carbon, as in there are no other predominant conjugate acid base species other than H2CO3, HCO3 minus and CO3 2 minus. That's what it means, right? Otherwise, as you remember, in alkalinity, when we looked at I think phosphate or such particular example, when we had other relevant conjugate acids and bases at high concentrations, we had to look at or we had to consider the effect of these bases on the alkalinity 2, right? Again, what is alkalinity? It's nothing but acid neutralizing capacity. So we need to look at all the bases. Again, I am just trying to refresh your memory here. And so obviously we have in alkalinity of a particular value and we have pH of a given value or a certain value, and so again what is the pH and dissolved iron concentration at equilibrium. So same case as earlier, but with a few other variables. So treat this as a closed system. So they are saying okay, don't increase the complexity, just treat this as a closed system, and then more or less based on the relevant aspects that we are going to look at here, we need to be able to comment on whether or not a strong base should be added along with FeCl3 in this particular scenario, okay. So let us try to understand the system here, I guess. So obviously pH was or is now 8.3 and there is also alkalinity. So let us say I am putting in iron in the form ferric iron in the form of FeCl3 from part A. If you remember that the pH dropped from for the neutral solution to 3.5, right, but in the earlier case the initial pH was 7, right, that is what we would presume, right, water, and also that it had no alkalinity. But in this case obviously the pH is relatively higher, 8.3, and more importantly alkalinity is present, as in the particular solution can neutralize any acid that is added to the solution. So you would obviously not expect such a great drop in the pH, right? That is something that we should be able to understand before we start our calculations, yes. And then let's see what we end up with and go through with that, and then try to analyze the system with respect to the effectiveness of the flocculant, right, FeCl3. So again first I am going to solve this by hand, but not in as detailed a manner as I guess we did it in the previous session, right. But we are going to set up the relevant equations first by hand and then obviously solve it by Vmintek, right. So I am going to go through with setting up the relevant equations in hand. So here though the key is that I already have pH and I have alkalinity, right. And what is the alkalinity now? You know that alkalinity is the acid neutralizing capacity, but here obviously again the key was that only the carbonate species are the relevant species. So we are only going to consider them. So what are all the bases present here? They are OH minus, right, plus HCO3 minus, right, plus 2 times CO3 2 minus because it can neutralize 2 moles of H plus, right, and obviously minus H plus, right. This is obviously the theoretical definition of alkalinity 2 if you can refresh your memories, I guess, right. So we have this particular piece of information. So obviously here what does the presence of alkalinity entailed, I guess, what do we need to understand from that? Obviously that means you have sources of inorganic carbon, right. So that means you need to come up with a way to find out what is the CO3 total, yes. So in the earlier example if you remember we only considered H total, Fe total and Cl total, right, which we obviously need to consider now right now too. But obviously an additional aspect that you need to consider is CO3 total. Obviously that is going to have some acid neutralizing capacity. So how do I find that? First we are going to solve this by hand obviously, right. So alkalinity, again I know this particular value that was given. I think I can change the units to moles, I guess, right. Molar units or equivalent units if required, right. And I think what is it now, 50 grams per equivalent, right, for CaCO3, and I can divide and get it in equivalents per liter, you know. Anyway, so alkalinity is a known value, and how can I express this equation as, let's see. So OH minus I can calculate because pH is given as 8.3, and I know that Kw is 10 power minus 14, that's equal to concentration of H plus into concentration of OH minus. So pH is given or H plus is given, so I can calculate OH minus. So alkalinity is equal to, let's say, what now, Kw by H plus HCO3 minus and 2CO3 2 minus, which I am going to plug in now, but first I am going to plug in H plus. So these two are known values, alkalinity 2 is a known value. Again we need to use some of our what do we say, dig into our knowledge base with respect to our acid base chemical process. So how can you express these species HCO3 minus and CO3 2 minus in terms of the variable that you want to calculate? And what's the variable you want to calculate? Obviously it's CO3 total. So if you can dig in, you would remember that we had ionization fractions, right, and that's nothing but, let's say in this alpha naught case, H2CO3 concentration by H2CO3 plus HCO3 minus plus CO3 2 minus, right, and that's nothing but being equal to H2CO3 by CO3 total, yes, and alpha 1 similarly would now be HCO3 minus by CO3 total, and alpha 2 would be CO3 2 minus by CO3 total, right. So obviously I am going to plug them in here, so it's going to be equal to 1 of alpha 1, I guess it's alpha 1 plus 2 times of alpha 2 into CO3 total, right. So nothing but HCO3 minus and CO3 2 minus alpha 1 plus 2 alpha 2 into CO3 total. So alpha 1 and alpha 2 again are constants for at a particular pH, right, and for the particular compound, which in this case is H2CO3, HCO3 minus and CO3 2 minus. So you can calculate pardon me, alpha 1 and alpha 2, right, and I can then end up with, I just have one equation and one unknown, so I can now calculate CO3 total, right. So with that I can calculate CO3 total. So until now obviously what have we done? We have just analyzed the system, but obviously there is one other aspect, as in you also need to calculate H total that's present initially, right. And what is H total present as initially now? Instead of writing the relevant what do we say, formation equations and then the tableau and such, obviously I am going to skip them here for now and then try to write them down here, right. So I know it's going to be equal to H plus minus OH minus, and what are some of the other species? Obviously H2CO3, HCO3 minus and CO3 2 minus. So for H2CO3 there is going to be 2 H, right, contribution, so it's going to be H2CO3 plus 1 times HCO3 minus, and obviously there is no contribution of H and CO3 2 minus, right. So thus I am not going to list CO3 2 minus concentration here when I am calculating the total component concentration of H plus, right. Again, what does this mean? Obviously by this time we should know that H will be in the form of either H plus, OH minus, H2CO3 or HCO3 minus. So even though the concentrations, individual concentrations of these species might change, the total H will always be constant, right. That's what we understand here. Again, so at this stage we have CO3 total, and from here again, because I have CO3 total, I can calculate H2CO3 and HCO3 minus concentration, right. I also have H plus and OH minus concentration, so I now have the concentration of H total, right. So initially now I have CO3 total and H total, right. So this is at the condition where the pH was equal to 8.3 and the alkalinity was, I think, 150 milligram per liter as CaCO3, right. Obviously the units are as CaCO3, it would be obviously better to have the units in the terms of equivalents per liter before you plug them in, right. And obviously the concentration units here in this particular formula would be the molar units. Why is that? Obviously because you are taking into account the equivalent factor 2, right, the number of equivalents for CO3 2 minus. So OH minus, HCO3 minus, CO3 2 minus and H plus would be in terms of molar units, but the alkalinity obviously would be in terms of equivalent per liter, right. Again, with that and the relevant background in our chemical process, we can calculate CO3 total, and using that we can calculate H2CO3 and HCO3 minus and end up with H total. So to this we are now adding FeCl3, the solid, right, and we are adding it at 10 power minus 4 molar, right. So now we need to understand how is the system going to change, right. So obviously now CO3 total, think of this now, we have CO3 total somewhere listed here. Did we list that here? Okay, we did not, so let's list that here. What is CO3 total equal to? You know, we did find it out earlier. What is it going to be present as? It's going to be present as H2CO3, HCO3 minus and CO3 2 minus, right. This is from our background in our acid base chemistry, right. Again, I am skipping writing down all the species and the relevant formation equations and the relevant tableau, but by this time you should be able to understand that CO3 total is only present in these three conjugate acid base forms, or the species are H2CO3, HCO3 minus and CO3 2 minus, right. So that is the case, but by adding FeCl3, do you see that you know, are you adding any source of, you know, this CO3 total? Is that being changed or no? No. So CO3 total is still going to stay the same, right. But what is going to change though? Obviously H total will change, as in the value is going to be constant. Why is that? I think to better explain, I had better write down the species. So earlier we had only H plus, OH minus, H2CO3, HCO3 minus and CO3 2 minus, right. And from this I have CO3 total and H total, right, and I wrote them down in the previous, anyway let me write them down here. So it is going to be equal to H plus minus OH minus plus 2 times H2CO3 plus 1 times HCO3 minus, right, and CO3 total would obviously just be equal to H2CO3 plus HCO3 minus plus CO3 2 minus. This was the initial condition, but after adding FeCl3, the solid, right, at 10 power minus 4 molar concentration, what are the new species now? I know that it will still be H plus, OH minus, H2CO3, HCO3 minus, all the species present earlier certainly, and also the metal, free metal, right, and also let the salt Cl minus, and what else now? All the other complexes, FeOH plus 2 charge, FeOH twice plus 1 charge, FeOH thrice, neutral charge, FeOH 4 negative 1 charge, and also the solid, right. So these are the additional species that I am going to have in my solution, because I am putting in or adding FeCl3 to my particular solution, which initially had only the carbonate species and H plus and OH minus, right. So this is what I have. So I need to be able to incorporate these aspects into my solution. So obviously now if I look at it again and write CO3 total, CO3 total would still be equal to, is there any CO3 in this particular species? Nope, right. So I am only going to go with the same case as earlier. It is still going to be equal to H2CO3 plus HCO3 minus plus CO3 2 minus, right. And keep in mind that we already calculated what this value was in the previous section, right. We already calculated what CO3 total was, and from that we already calculated what H total initially was. So we already have the initial value of H total, let us say X, right, and let us say CO3 total was equal to Y, we already calculated that. And here by adding FeCl3, right, if you keep in mind, now the tableau is CO3 total, Fe total or CO3 2 minus, Fe3 plus and H plus and Cl minus, and I list all the species and formation from the formation equation blah blah. I am not going to list that. And if I write down the recipe species here, is CO3 2 minus affected here? No, right. Fe3 plus, yes. Is H plus affected here? No. Is Cl minus affected here? Yes, by 3 times, right. So what I am trying to show is by addition of FeCl3, you are not changing the CO3 total, nor are you changing the H total, right? But within H total, so a CO3 total is still, what is it here, Y, right? It's still equal to Y. But H total now is no more just equal to this particular set of variables though, right? But because as you see FeCl3 does not entail any increase or effect on H plus, it's still going to be equal to X, but the number of variables or species are going to change. And what are they? H plus minus OH minus, pardon me, plus 2 times H2 CO3 plus HCO3 minus, right, and plus the relevant species here. And what are they going to be equal to? FeOH plus 2, but obviously it can't be plus from our part A. If you remember that, it's going to be minus because it's OH here, right, and minus 2 times FeOH twice plus 1 charge, right, minus 3 times FeOH 3 neutral charge minus 4 times FeOH 4 negative charge, and again minus 3 times the solid that has precipitated out, right. And again, what is this still equal to now? It's still going to be equal to X plus 0 times of FeCl3, this solid, right. And why is that? As you see from your particular balance equation, addition of FeCl3 causes no further change in H total. So H total is still going to be equal to X that you calculated earlier, but obviously you are now going to have additional what do we say species, right, and there are 1, 2, 3, 4 complexes and 1 solid phase, right. So again keep in mind that you are adding FeCl3, that does not change. Let us say earlier H total was, let us say 10 power minus 4, just for an example. Let us say by adding FeCl3, as you see from your total component balance here, there is no source of H plus in FeCl3, right. So the H total is still 10 power minus 4, but this is now distributed over a few more species, as in a few more complexes and the solid too, right. Earlier H plus was only present as H plus OH minus H2CO3 and HCO3 minus, but now H plus is also present in the form of all the FeOH complexes and the solid, and that is what we have just identified here, right. So what do I have here? I still have CO3 total, right. I have H total which is still equal to X, and these are values that I calculated, they are not unknown values, keep that in mind, right. So I have CO3 total and H total, and I now can calculate Fe total 2, right, and Cl total 2. Yes, and Fe total, I guess I calculated that from last time, so I am not going to go through the relevant what do we say write up, but I am just going to list the equation here. Fe3 plus what else? FeOH plus 2 charge plus FeOH twice plus 1 charge, FeOH thrice neutral charge plus FeOH 4 negative charge, right, and the solid, right. Again the assumption here that I am going with is obviously that this solid is formed, and which we know will probably be formed from our particular what do we say background from part A2, right. So this is it, and what is this equal to? That is equal to 1 times FeCl3 naught. So 1 times FeCl3 naught, as in what we are putting in initially, that as you know is equal to 10 power minus 4 molar, right. So same case I can write Cl total, it is just equal to Cl minus concentration, that is equal to 3 times FeCl3 that I am putting in initially. And what is that? Why is that? Because it's 3 times here FeCl3, right. That is equal to 3 into 10 power minus 4 molar, right. So now again it's same case as earlier, I need to now list beta 1 star so on up to beta 4 star, right, and obviously Kw and also K solubility product for this particular solid ferrihydrite, right. So again, it's similar to what I had earlier. I have the relevant number of variables and I need to come up with the relevant number of equations. So for that, I am going to look at the various equilibrium coefficients or solubility products, and then as we did so in part A, we can then go ahead and calculate the relevant number of unknowns that you want, right. What can I do from here, let us say? So I can minimize the particular equation such that, what is it now, that I am going to end up with just two equations in H plus and FeOH thrice solid. And what am I going to use to minimize them? I am going to use beta 1 star to beta 4 star and the two equilibrium coefficient related Kw water dissociation and solubility product for this particular solid, and come up with two equations and two unknowns and solve for them. And once I solve for them, obviously I can calculate pH, and once I have this solid, obviously Fe total in the aqueous phase will be nothing but Fe total minus Fe total in the solid phase, which is what we just calculated, right. And obviously that is what the question asks for, right. Again, keep in mind what is it that we have been up to. First we analyze the initial conditions and calculated the, so let us just summarize what we have been up to. So initial pH was given and alkalinity was given, right. So from this we ended up calculating CO3 total initial and H total initial, right. So we have these two values, and then because of plugging in FeCl3 solid, we see that there is no further change in CO3 total or H total. So they are still going to be the same values that we had earlier, right. But now we are also going to have Fe total and Cl total, right, which we have from FeCl3 as 10 power minus 4 addition, and then we solve for the relevant variables and get the total iron concentration which has precipitated out, and also the pH, and then calculate the relevant variables from that. So again, this is for your purpose of understanding. Obviously by hand, even though you use Excel, let us say, it is going to take you or is relatively more time consuming, right. So now we are going to solve this by Vmintek. So let us see how we go about that, right. So let us move on to Vmintek. So first I need to plug in the pH, and that was at 8.3, right, 8.3, and then I need to specify for alkalinity parameters and alkalinity, and where is that here? It was milligram per liter as CaCO3, and it was 150 if I am not wrong, 150, right. And so I am going to say OK and just run Mintek, right. And if I look at equilibrated mass distribution, I can get the relevant H total and CO3 total, right. Let me write this down so that I need them later. So it is 2.99 blah blah into 10 power minus 3. Let me write that down somewhere. So CO3 total comes out to be what now? 2.99 into 10 power minus 3. I will list that as 3 into 10 power minus 3 molar concentration, right, or 3 millimolar, right. And what was H total equal to? So 2.99 into 10 power minus 3, which I will approximate by again 3 into 10 power minus 3 molar, that is equal to 3 millimolar, right. So obviously if I wanted to I could have also looked at the sum of CO3 minus H2CO3 and HCO3 minus, as I did earlier, but obviously you can also look at equilibrated mass distribution and go through with that, or just for sake of understanding, let us see if that is going to be the case or not. Here I am going to try to calculate CO3 total here. So I will print this to Excel and let me try to calculate CO3 total. So that is going to be equal to CO3 2 minus concentration plus H2CO plus H2CO3 plus HCO3 minus, and enter. So that is again equal to, as you see, 2.99 into 10 power minus 6, right. So or 3 into 10 power minus 3, which is what we had from that equilibrated mass distribution. In the same manner, let us try to calculate H total. So H total will be equal to H plus minus OH minus plus 2 times H2CO3 plus HCO3 minus, and enter, and again that is what you see here, that it is equal to 3 into or 2.99 into 10 power minus 3, which is what we have from our particular Excel in the equilibrated mass distribution, right. Again these are values we are now going to note down, I guess. So back to main output menu, back to input menu, and now what do I need to do? I have H total and CO3 total, and now what else do I need to do? I need to plug in the aspects for Fe total and Cl total, and also mention that the ferrihydrite is a possible solid, right. So let us do that. So before I do so, I need to say that alkalinity is not going to be listed because I am already considering CO3 total as a particular species. Just to be on safer side, I am going to reopen or restart vMinTech, okay, and pH should now be calculated from mass balance, right. So what else now? I need to plug in H total, and where is H total? Here, H total, and as you remember, I think that was 3 millimolal, right, that was 3 millimolal. I am going to use the millimolal units and the key here, and that is 3 millimolal, right. So I am going to add that to the list, and same case with CO3 total, and that is again 3 millimolal, I believe, add that to the list, right. And now I need to plug in the values for Fe total and Cl total, and if you remember, it is equal to based on FeCl3 that you are plugging in initially, that was 10 power minus 4. So I am going to plug in Fe3 plus initially, and where is Fe3 plus here, please? Fe3 plus. So I think we are going to go with millimolal units, right, and it is now going to be equal to 0.1 millimolal, right, because it was 10 power minus 4 if I am not wrong. And now I am going to add Cl. Cl was 3 into 10 power minus 4, right, so it is 0.3 millimolal. So I am going to add that to the list. I am going to just confirm the components here. H plus was 3 millimolar, CO3 was 3 millimolal, and I am putting in FeCl3 at 10 power minus 4, right, or 0.1 millimolal. That is why Fe3 plus is 0.1 millimolal, and Cl minus is 3 times that is going to be equal to 0.3 millimolal. So back to main menu, and obviously I need to specify that precipitation is feasible and that a particular or the solid that it can precipitate out is as ferrihydrite, and I am adding that to the list, right, and go back to list of possible species to see that it is included. Yes, it is included. Back to main menu, and now I can run my MinTech, and what do I see here? Obviously that the pH now hasn't fallen down to 3.5 or so. The pH is now at 7.28 or 7.3, right. So why is that now? That is probably because of alkalinity. And why is that? Alkalinity means its acid neutralizing capacity, or alkalinity consists of the bases in the form of HCO3 minus and CO3 2 minus. Obviously CO3 2 minus does not play a huge role at 7.3 or 8.3 pH values, right, but HCO3 minus should have been at considerable concentrations. So let us just look at that. Let us say view species distribution. So as you see, considerable amount of CO3 2 minus is present as HCO3 minus, and HCO3 minus obviously would have taken in or or neutralized any H plus that would have been formed due to the addition of Fe, right. What happens when you add Fe3 plus? FeOH complexes are formed, thereby releasing H plus, right. So this H plus though can be neutralized by the HCO3 minus that is going to be predominant at this particular pH, and so thus unlike in part A, if you remember that our pH fell from let us say fell to 3.5, but here from an initial pH of 8.3 it fell down to only 7.3, right. And why is that? Because we had alkalinity which has some acid neutralizing capacity in the solution. So again let us go back to our particular case and look at equilibrated mass distribution, or okay, before that amount of finite solids present. So ferrihydrite is present at 10 power minus 4 molar. What does that mean? So keep in mind that FeCl3 and Fe total in that case was 10 power minus 4 molar or 0.1 millimolar, right. So here from amount of finite solids, we see that ferrihydride concentration itself is equal to 10 power minus 4, right. What does that mean? That all the solid has precipitated out more or less, right. So let us look at that equilibrium mass distribution. So Fe3 plus, so if I look at that, it means almost, not almost, 100% or almost all, I guess it can never be truly 100%, right. So because it's equilibrium, you will always have some free metal or some complexes present in the solution. So almost all the particular Fe3 plus has precipitated out, that is what you see here, and little to none is present in the dissolved form, right, and that is what you would obviously expect here, right. And back to main menu, and different kinds of species, but they are all going to be at relatively very low concentration, right. Why is that? Because iron almost 99.99% or 100% has precipitated out at as ferrihydrite even at pH 7.2, right. So let us go back to our particular case. So I think here what else did we plug in? We plugged in Fe total was equal to 0.1 into 10 power minus 3 molar, and Cl total as 0.3 into 10 power minus 3 molar, and we mentioned that ferrihydrite was a possible solid, and with that we calculate the pH to be 7.28, right. This was for part B when we had alkalinity, and initial pH was 8.3, but for part A when we had no alkalinity, the pH dropped out to be, I think, around 3.5, right. So keep that in mind. And I believe the Fe total solid was equal to, I think, 97% of the Fe total, if you remember from our previous part A, right. Fe total solid was 97%, I believe, of Fe total, and in this case though the Fe total, the solid that has precipitated out, is almost equal to 100% of the Fe total, right. Again, what is that, where is that from? Obviously we saw that from here, that 100% of it has precipitated out of the total Fe total, 100% has precipitated out. So that is what I am trying to illustrate here, I guess, right. So compare that particular case. So not a great deal difference in the amount of precipitation, 97% or 100%, but the key is that the pH does not fall down to a very low value, but it is at the relatively neutral pH range, right. And why is that? Again, that is because alkalinity and HCO3 minus can neutralize any H plus present, or that is produced due to the addition of your particular source of Fe3 plus or the complexes, right. So that is what we have here. So again, one aspect that we need to now understand or look at is, why are we adding FeCl3 in the first case? So because it can act as a flocculant, right, in the coagulation and flocculation process. And here obviously we need to understand the system, and also the key here is that for this particular case, when the pH end up to be 7.2, right, treat the water, comment on whether or not strong base should be added along with FeCl3, right. Usually let us say if there was no alkalinity and the pH fell down to a very low or acidic value, then you would have thought of adding maybe some OH minus, let us say, right. But even in that case you need to see if that is going to be beneficial. Why is that? So here the key is to understand obviously what we talked about earlier. So how is this particular mechanism going to work? We know that there are two aspects or three. There are going to be charge neutralization, right, as in the colloids are negatively charged, right. So any positive charge that you add, that is going to neutralize these colloids, I mean the charge on these or net charge on the colloids or suspended particles, allowing them to overcome their forces of repulsion, I guess. And the second aspect is sweep flocculation, as in now you have these FeOH thrice solid that precipitates out, that is what you saw here, right. So these particles, right, are either going to aggregate on the existing suspended particles and create a bigger particle, allowing it to settle down, or they themselves act as, let us say, adsorbents or sites for the other particles to be entrapped on them, let us see, right. So sweep flock mechanism, I guess, right. So either sweep flock or charge neutralization, and I believe we also came across the term co-precipitation in the last couple of classes, right. So here the question is, if the pH is already 7.2, should you add more of a strong base? I would say not. Why is that? Because let us say if you keep adding OH minus, right, then Sweep flock, won't be affected because anyway even at 7.2 pH we had 100% precipitation of the particular iron, right. So, sweep flock there should not be any further change even if you increase the pH, right. But what happens if you keep increasing the pH from 7.2, let us say, right. So, you are, if any, right now you have little to no charge neutralization, right, because all the Fe3 plus, right, has precipitated out. So, any complexes that are present, let us say, we can look at that here. So, the complexes are present, all the positively charged complexes, right, they are present even right now at very low or remarkably low concentrations, right. Yes, but as you keep increasing the OH minus concentration, what would happen now, even these low concentrations, they would now the net positive charge would keep decreasing, right. So, FeOH twice would now go to, let us say, FeOH thrice. So, the positive charge would be neutral, or FeOH thrice can go to FeOH4 negative charge, and so on, as in you would increase the negative charge or decrease the net positive charge, right. So, charge neutralization, if any, right, if any out there, the purpose would be defeated if you add the base, right. So, again sweep flock is not going to be affected when you add the base, but the pH will further increase, and defeating the purpose of charge neutralization, if any, that is occurring in the system. So, obviously for this particular scenario you would not add the base, but obviously maybe if the pH was very low, right, you can consider that particular addition of the base, right. So, again with that I guess I am done for today's session, and I believe we are going to look at a few other aspects, as in until now we only looked at precipitation of one solid, but in general though it will never, not never, let us say, you can have more than one particular solid precipitating out, right, as in CO3 2 can precipitate and CaOH twice 2 can precipitate, let us say. So, we need to see which particular process will be the controlling process, I guess, right. So, we are going to look at competing precipitation or competitive precipitation in the next session, and I guess with that we should be done with our precipitation and dissolution aspects, and then move on to the redox process, right. So, with that I guess I will end today's session, and thank you.